going to go over the class, getting the most from your digital multimeter. You can call it digital photometer, multimeter. Most of the newer information we have out there calls it digital multimeter because it does multiple functions and it used to do that. When I first started, it was called a voltmeter. It's a little bit different. On the webinar objectives we're going to do today is we're going to go over how to choose a DMM. And the biggest thing about it is, if you're teaching out there, you might have two levels of digital multimeters you're going to use. You might have an inexpensive for some of the newer guys, and as you're teaching them along and teaching what they can do with the meter, you're going to move over to a more advanced digital multimeter for use. We're going to check the DMM for accuracy, and that's a real important factor because sometimes you can have problems with the leads, problems with the unit, and it gives you wrong readings you need to look at. We're also going to go back over the voltage drop testing. This is critical for all of you to teach the student to understand voltage drop because it's one of the biggest items that we're going to use in diagnostics. We're also going to be able to look at sensors. So we want to be able to check the sensor in 3 wires to it. We want to check the power, ground, and sensor output. Those are 3 components you need to check. We also need to be able to do some duty cycle, frequency. We need to check frequency. We want to check min-max. And some of your meters will actually have a peak min-max, so we can actually read the multiple voltage or the maximum voltage on a circuit. It might be an injector you might look at. We also want to be able to look at the power, the grounds, and we're going to do some bus testing. And bus testing, we're going to be able to look at the terminating resistors in the bus. But the biggest thing you must look at all times is make sure you have proper ground, proper voltage, and the proper signal, something you need to always look at for information. And we're going to also go over how to use your DMM to make sure the circuit is working correctly and prepare you to learn to use other tools to help in diagnosis. So we're always know that your tech is going to be learned, or your student's going to be able to learn how to use your scan tool. Well, the next thing they should do is verify that everything's working out. If they have a sensor or a code set, we have to verify that with a digital multimeter. That's where they should start. Entry-level DMMs are capable of measuring, if you look at it, AC, DC voltage, millivolts, most of them are going to have a millivolt scale, conductance, that's ability to what? Allow things to flow through, continuity, making sure you're there. A lot of the continuity meters, you have to actually push a button in order to get them to do that. And we have amps or milliamps. Resistance checks, most all of the meters will do that. And we have capacitance, that some of them will do it, some of them won't on your entry meter. And then the microamps and diode tests. Well, I'm taking this little one here, and if I look at what I've got, I have ohms, I have amps, and I have AC voltage. That's all this meter does. This is a basic meter that you might see. Notice the size up there. This is very cheap. It's like 40, 50 bucks. That same unit can be up to here, and we're going to add in different components we can do in the testing. So that's beyond the entry meter. Now, if I was looking at the meters also, we're moving up here. Each meter is going to be a little bit different. So these are going to be basic, but the problem about the basic meter is it's not going to do what you need to do for diagnostics because we have to add a couple other things into it. So if we look at this slide that we have up here, we should look at the additional things that come up there. So if I'm looking at it, you need to be able to do frequency. Why would you want to do frequency? Because you might want to do frequency on an input. Mass airflow sensor on a General Motors product is frequency. You might also be looking at most of the new mass airflow sensors on top of that are frequency. If you look at the other thing, you might want to do RPM. There will be an adapter somewhere so you can do RPM on the engine. Why would you want to do that? If you're cranking the engine over, you want to see the cranking might be 200 RPM. You want to know what you have, and you have an RPM. The temperature sensor. If you're using the temperature sensor on there, you're doing AC work. Most of the AC work, if you're using your temp gun doesn't always give you accurate readings. So it's a really good idea to have the ability to actually touch the component you're testing, or the tube or the inlet tube to the AC system, and be able to actually read the temperature that way. That's why a lot of these have little adapters that you can get in and get the temperature on the sensor, or on the line or whatever for diagnostics. A lot of times you do before and after a component, like before and after CCOT, if you're looking at the other processes. The other thing you might want to be able to do is duty cycle. So if you're doing a duty cycle, you might want to check that. Your scan tool says a certain duty cycle, you might want to go out and check it. Let's say a purge control solenoid would be duty cycle. You want to look at that. The other thing you're going to look at is pulse width. We can test an injector with pulse width. That's real easy. I wouldn't be able to do it this meter here at all because it's not going to give me the ability to do it because this is the cheap entry level meter. And it doesn't even meet my entry level specs. I'd probably be going over to more expensive meters to get that information. This one here, I have millisecond pulse width. I actually have the ability to read it. Now this is a little bit more expensive than this one, but it gives me information. So you have to know your meter and what you're looking at. The other thing is, when you're buying a meter, if at all possible, get the specs before you buy it. So the specs are going to be somewhere in your manual. And I know all of your instructors and your students have read the manual for the digital photometer. Yeah. Be honest with you, this last weekend, before I came in here, I read the manual cover to cover for 3 different digital photometers I had. And there were features in there that I didn't even know were there. And I've been using these meters for over 10 years, some of them. So again, it's a good idea to read the manual. This is one of Fluke. Some of the manuals are not very big, real quick read. So again, if you're looking at your meter, you want to know this information. The other one you look at is the frequency or the accuracy of the meter by looking how much percentage plus or minus on sensor readings or voltage readings that you're looking at. So a lot of things to look at when you buy a meter. This is the next most important thing you're going to buy versus your scan tool to start off with. Then you're going to move into your lab scope later on, and that's going to be another expense. But a lot of times, your meter will be what you need to do test a circuit. So that's where we're going to start out. Now we're going to go on and do some testing on different circuits as we go across. All right, we're over to the board right now. We're going to look at the meters. First of all, you're going to notice both of my meters are in ohms up here. Notice the screen's a little bit different depending on the meter. First thing I need to do, I'm going to pick up my leads over on this side, and what I'm going to do is make sure you do something. You always want to make sure the one that's got the best lead set up. So I'm putting it on here. Now, if you notice something right at the moment, I've got 0.1, all right? But if I wanted to get rid of that 0.1, if I wanted the 0 leads, I would hit relative on this particular unit, and it would take that reading out, and it didn't take that reading out. Let's hit it again. There we go. Takes the reading out, and it makes me back to 0. So whatever I do, it took out that 0.1. Now, if I go to my other meter on the other side over here, it's a little different. Every meter's slightly different. So if I'm looking at this one, I'm going to hold these together. And if I hold these together, you shouldn't really put your finger on there, but if I hold these together right now, I'm going to turn my meter back off and put it back on. And at this point, I've got 0.2. Now, on this particular meter, I have a 0 up at the top. If I hit 0, it takes that out, and now we're at 0. So we have to know that our meter leads are working. It tells me 2 things. My leads are good. On both sides, leads good because they're less than 0.2. If it's 0.3, 0.4, 0.5 or higher, then I would go immediately and think I need to replace my leads. This one shows it's working fine right now. The next thing I'm going to do is this a little weird, but I have a 1 ohm resistor. And the reason I have a 1 ohm resistor is a lot of times when you're disconnecting battery cables on a car and you want to shut all the memory down a car, a 1 ohm resistor is a real good idea to use. So I'm just going to put this 1 ohm resistor in here. And I came up to 1.1 ohms. So in other words, it's supposed to be a 1 ohm resistor, but there's a little variation. So we notice right now it's at 1 or close to it, doing kind of like that. So I know my meters were reading properly. Those things are doing a good job. Now, if I go over and I want to do some other testing on this, one of the other things I might like to do, if I've got ohms on that one, and I'm going to go over and hook the leads together. So if I'm hooked the leads, black to black, red to red, and I'm just hook them up over and lay them up here. Notice they're both in ohms. The minute I take this thing over and go to voltage, I read on this particular ohms is 1.25 volts. Now, that means when I'm checking a circuit with an ohm meter, I'm going to put 1.24 volts across. If I take this thing and put it back in ohms and flip this one over to voltage, notice what happens up here. It says 2.65 volts. So, but at the same time, notice what I've got at the top. I've got 10 mega ohms. So that means my impedance on this meter is 10 mega ohms. If I take it and reverse it again, put voltage, put ohms, notice it doesn't read exactly, but it tells me on this meter I get 10 mega ohms. So I know these 2 meters are within reason. Now, if I'm doing this, and I've had this happen with doing some classes where I've actually done the class, and one of the meters read 5 mega ohms, which means that meter shouldn't be used in diagnostics. The other thing while we're here, we're just going to flip this meter over here. Let's just come up over here instead of diode testing, we had that. let's go over and do a diode testing up here, and I'll need my voltage on the other side. Notice that diode testing, I'm at 7.33 volts, which means I'm doing a proper reading up there. I have to have higher than that. So a diode has to be triggered by about 6 volts or better. But if you look at the ohms reading, the reason I'm bringing this up, if I'm testing a circuit with an ohm meter, I'm really not stressing the circuit at 1.25 volts, and I got a 12 volt circuit. So out of curiosity, I'm going to flip this one over, and I'm going to do voltage, and I'm going to flip this one over, and I'm going to do diode testing. And now at this point, you notice I've got 3.78 volts. Your meter is always going to read slightly different. Some of them put even higher voltage up there. So I got 3.78 volts this meter puts out to test a diode. Notice the difference in the two meters. You have to be familiar with this. So a lot of your students will try to check a diode with a ohm meter test. Ohm meter test is not strong enough to trigger that diode. This way it is. So we're looking at, again, 3.78 volts. I flip this back over to voltage, flip this one back over to diode, and notice this one puts out 7.3. So I need at least 3 or so volts to do it. So these are some really quick tests you can do on your meter to see if it's working properly. In other words, if I don't have that 10 mega ohms we had before, if I put ohms on here and we did this one, and I'm going to put it on voltage on this one, notice if we look at it, 10 mega ohms, and there's my voltage. I'm testing my meter to make sure I have proper ohmage. So if a guy buys a cheap meter, which a lot of guys will do, and they bring it in, those are the ones you pull out of your pocket, you might get at particular places, freight stores, and you put out a cheap meter, you're going to have an issue. This is a real way to check the meters if they're reading correctly. It gives you a good idea. If you don't go through some of this, you'll have a problem. Now, the next thing I want to do, and I'm going to do it a little differently, I might even have to change leads. All I need to do is really take off my black lead, and I dropped it, I'm sorry. And if I take my black lead, and I'm going to put it in ohms again. Now, if I put my black lead in ohms, I'm going to check the fuses in this meter. This is what you can do with this particular meter, and it says 0.2. Notice we have that nice little button kicking on us. If I take it over to this one, I have it open, all right? Interesting. So I'm going to take these leads off, flip it over, this lead over to this side, because you can't get in a little easy. This is when these kind of leads are better. The other neat thing about these leads, if you want to, you can just plug them in like that. And it says lead, but the main reason, because I was what? In the wrong area. So again, it says 0.2, and it tells me my leads here. I could also come up and do this other side, and it tells me what? Have almost one. Again, let's turn it back off. We'll start it back again. This one's a little bit unique, but if you notice when it does read, it's going to read almost 1 kilo ohm. This one is going to read, when it reads, it says the leads, it's telling you got a problem, it's 0.2. So it's telling my leads are incorrectly set up, but that's good. Now, if I'm doing this again, let's come over here. Different meter. It beeped. This time it's beeping. I got 0.2, all right? I go over here and touch here, or put this in up here, I got open. That tells me that the fuse for the milliamp on this particular meter is blown, so I'd have to put a new fuse in it. Real quick way to test it. Not all the meters do this, but the Flukes do it real well. I've tested a few other meters. They will do real well on the amps. They might not be easily determined if you have a milliamp reading, but this is a real quick way to test if your fuses are good if you have a Fluke meter. Saves you a lot of time and gives you a chance. If you got a student's got some wrong readings, you can actually look at the information. All right. So we're going to move over to some more testing. When you're doing circuit testing, we have 2 pictures up here you can look at. The one on your left would show you how the circuit is actually working. So it shows you the components. It gives you an idea for your student to understand what's actually going on in the circuit. So we're starting off, we've got a protection device, which we always should have a protection device in any of our circuits up there. You have to prevent something going directly to the ground. We have to have some kind of load device or control device, which is going to be a switch, a transistor, or other ways of doing the process, and then we're going to look at have a load or multiple loads being on circuit. This is a simple series circuit. If you go over to the one on the right side, you see that you have 12 volts, and then we're going to go to our circuit protection device, and then we're going to go to our switch, and then we're going to go down to our load on it, which is 14-volt bulb on here. So the biggest thing about it is you need to be able to break the circuit down and look at the wiring diagram. So when a student or a tech goes out to work on a car, he should have the wiring diagram up already, because that way he gets an idea what should be on what wire. So if I'm looking at the circuit on the left-hand side, it tells you what should happen. If I go to the right-hand side, I know that I should have voltage being fed, 12 volts being fed all the way to my load. If I have any loss in there, which we can't have a slight loss, that would be a voltage drop because we use up a little of the voltage. So that's the first thing you're going to look at on circuit testing. You must understand what the wiring diagram is, and you should get a visual idea of what should be at each point in the circuit. It makes your diagnostics a little bit better, and it makes your teaching a little bit better, because you're going to have a student that actually can look at the information, decide if it's good or bad, because he has a roll map or has a drive map that he's going through this process. Now, there are different types of voltage testing you look at. So the first one's open circuit voltage. That means no work is being done. And we're going to do a lot of that on our battery. We're going to test the battery for open circuit voltage to make sure there's a proper charge in the battery and it's available to do its work. So that's the first thing you're going to look at. The next thing what we're going to do is voltage drop testing. Now, there's all kinds of ways this is described to everybody, and this is a little bit of a problem with some guys describing and understanding what you're doing it. Realistically, voltage drops are being used up or consumed in the circuit to go across. So when I started a circuit, I might have 12 volts here, but at the end of the circuit, I'm going to have no voltage left over or slight voltage left over. That means we're going to be able to check it. Now, the opposite of this is if we're looking at current. Current will be the same no matter what it is through the circuit. So any resistance is going to use up some of the voltage. It's going to transform it into heat or into light or into something else going across. So that's two different styles. So right now we got a little circuit up here. I have 12.08 on my meter up here. This is a 12-volt battery, so that should be okay. I hear that from a lot of techs and little students. No, because the battery should be about 12.6 volts. So this battery tells me right now this battery should be actually recharged because I'm less than 50%. If you ever look at your charts, you want to make sure your students looking at charts to see what the voltage should be. Is that an accurate test? The answer is yes. It tells you the state of charge or the potential voltage you have in the circuit to work with. And all electrical testing should always start at the battery, no matter what you're working on. If you're working on a body problem or a chassis problem, anything that's electrical, you should always make sure you have proper voltage to the battery. At this point, I would probably want to charge this battery for a while to get it up to the 12.6. And if you're looking at charts, that will break the voltage down. So this one is telling me I need to charge the battery and make sure it's working properly before I go on. We're going to do some voltage testing. In the process, we're going to give you some information you should use when you're teaching this or a tech's actually doing its diagnostics. First of all, you're going to check voltage. You're going to have to be in parallel. You never do a voltage in series. Only amperage is done in series. Parallel is what we're doing. So we're going to put our meter across the circuit and we're going to measure the voltage as it goes down. Now, you can start at the bottom, you can go up, or you can start at the top and go down. Depends on how you feel comfortable about your testing. I tend to start at the battery first to make sure it's proper, and then I go at my fuse or my circuit breaker or something like that. I want to make sure I have the actual voltage I need to work on the circuit. Then I'm going to flow that through. If there's a switch or a transistor, I want to make sure I have the proper voltage of that. So you'll see in the one little curved line at the top there. Now, if I keep on going down on this one, I'm going to go up to the switch. That's a switch up there. I want to make sure that it's working properly. I'm going to check it open and closed because it does make a difference. And I want to make sure I have the proper voltage to my solenoid or my load device, whatever it is. It could be a light. It could be something else in the circuit. Now, I call this a natural point break of the circuit. So what I normally do is I check my battery voltage or my voltage supply somewhere before all the fuses and everything. Then I'm going to check my supply voltage to my load. At that point, I know that if I have proper voltage to my load, then I know that I have a good feed circuit coming all the way back to my source voltage. Now, at the same point, I'm going to take my lead, and the next thing I'm going to do is take my lead after my load, and I want to make sure that all the voltage has been used up. There might be a little voltage left over, and we're going to show you some voltage drops that you might see, some correlations in the voltage. If I'm doing everything, if I use all the voltage up here, the circuit's working properly. If I don't use all the voltage up, then I either have a ground issue or I have a load issue. This is a real quick way of doing it. Again, I'm only moving my red lead 3 times. I'm moving it to my battery. I'm going to have a good ground. I'm going to do before my load, and I'm going to do after my load. And that's the way you should do it. If I have 2 loads, I'm going to before my load and after my load, or individually if you want to do that. But that's a good way of breaking the circuit down and teaching the student. They have to break it down in order to do what they want to get the most information they can out of the circuit. Now, if I go over to my next circuit up here, or my next screen up here, we're going to talk about some voltage drops. And voltage drops still is confusing to a lot of people. It's still confusing a lot of techs out in the field. So what you want to look at is the resistance in the circuit is going to create, they're going to convert that resistance, so it's going to create a loss of voltage. They're going to create it, they're going to turn it into heat, light, or motion if they're doing something. And you have to have current flow. If you don't have current flow, you're not going to have a voltage drop. I see a lot of guys trying to test a circuit with the circuit off. Continuity, yes, but you're not going to be able to do a voltage drop or current flow. It does not work. Your circuit has to be active in doing that. You've got to teach that to everybody. And the amount of voltage drop is going to be the difference on it. So you're basically going to do a voltage drop. You're going to hook up before a component and after a component. And if you do that, you should be able to see the voltage that is being used by that component. It should be very minimum up there. You'll see some people say that you should have no voltage drop at all in the circuit. That is not correct. You will have some voltage across a connector, across a resistor, across a wire itself. Sometimes you'll have a little bit of a voltage drop. We do know that occasionally we're going to have connection problems on circuits because we're going to have where they're not feeding together correctly like this if I do the circuit. So you need to look at a circuit and compare it and go down the line. Always do the voltage drop in the circuit to see where you're losing voltage before your load. That's our process. Now, the total current flow to and from the source should be the same. So if I'm going across up here, voltage will drop as you're going down the circuit. Current will be the same. No matter where we're at, the current will be the same. That's something a lot of guys have a little problem with. But it's really easy to look at. Voltage is being used up, current is doing the work. Simply way to think about it. So I'm going to go to my next slide up here, and this is some voltage drops suggested allowed values. I'm going to tell you these are suggested, but I would tell you is if you've got the information from the OEM and it has a certain voltage drop that you're looking at, use that instead. So if you look at it, across the connection, there should be 0 voltage drop. It should 0.2 across the wire or cable, 0.3 across a switch, and sometimes you're going to see more. If you see more than that, you know that switch is starting to go bad on you, or you have a bad connection there. 0.10 or 1000 millivolts on ground, or 100 millivolts, excuse me. If the value is not listed, guys, use the service information. Now, a 5-volt circuit does not follow those guidelines. Normally, we're going to do 50 millivolts on the ground side, or the voltage drop that we're going to see on a 5-volt circuit. You'll see some people allow 70 millivolts. Whatever you want to look at, guys, it's up to you. So if you're going to use it, I would have always used the manufacturer specs if they're there. If not, there's the generic specs you should use. Measuring resistance or using your ohm meter. We've got to talk about this a little bit differently. First of all, a lot of people, or techs and students both, try to use an ohm meter with a live circuit. The circuit must be off to use an ohm meter. You'll either damage the ohm meter, or you could have other things that you would have, like problems with the circuit itself. So the first thing you need to do is make sure the circuit is dead. The circuit must have no voltage flowing through it. The components you need to check, a lot of times it's really easier. Let's say I've got a purge solenoid or some kind of solenoid on it. I want to remove the connector off of it, or an injector for that matter. I want to remove the connector off and actually isolate that circuit or that component in order to look at it and measure the resistance of it. So again, when you're checking an injector, you're going to have to disconnect the connector on it and do it. A lot of people try to do it with it connected. That's not a good idea because you pick up other resistance in the circuit. The other thing is, if you're ever going to work on a live board or a circuit, if you need to disconnect one of the leads to the circuit itself or the component itself, the reason you have to do that is you're isolating that component. If it was still on the board, when I'm doing some repairs on computer boards, if it's still on the board, I'm going to pick up resistance from other circuits. I want to isolate that component, so you're going to have to remove one wire. And a lot of times if you're teaching your students that they're building little boards or whatever, you have to actually literally unsolder that circuit to make it work. The other thing is resistance is always checked in parallel. And another thing I want to make sure you understand, I don't use my ohm meter that much as I used to. Main reason is I don't use it unless there is a spec. So an injector, I'm going to have a spec. There might be 12 ohms. Let's say the per solenoid is 20 ohms. I know I have a definite thing or specification I need to look at. That way I know for sure if that component's working properly or not. Now the next thing you would want to do is maybe go back and do your current testing, make sure it's working there. But again, if you're doing resistance, the circuit must be off, and you're going to disconnect or isolate that component or that particular part of the circuit to make sure you're getting the proper ohms meter readings out of resistance in the circuit. You're using your meter and you're measuring current, you're going to have to move the leads over. So if I was looking at a circuit, again, I'll bring this up here. If you're looking at your red lead here, it's probably going to have to move over to here as it shows you there. So we're going to have to move the lead over to measure current. Again, if you're doing current, you're going to have to move the lead over. If you don't, it's not going to work correctly. So again, voltage or resistance, there's your current. So you want to move that lead over to do the proper testing on the circuit itself. The other thing is, if we're doing this, we need to be in series with the circuit. A lot of you start using the low amp probes or the amp probes. Well, that's a different circuit. They're going to measure the inductance around it, pick up the voltage that way. But if you're doing it with a digital voltmeter or the DMM, whichever way you're going to use your diagnostics on it, you're going to call it, you have to be in series with the circuit itself to measure the current. So that makes it a little bit easier to understand. The lead has to be moved. That's one of the first things. And the other thing while there, what's the other thing we should do? I talked to you before. I better make sure I check the fuses to make sure they're properly working before I start doing my testing. And again, that's it. The lead has to be moved. We're going to check our fuses, move the leads, then we're going to hook in series with the circuit, and we're going to check the current. Now we're going to move over and do some live testing on the circuits. This is the Electrical Skill Development Troubleshooting Model 5810TT is right here on the board up there. Look at it. This is the board we're going to be using for some of the testing. The first thing I did is laid out a simple series circuit. So my red lead goes over to my circuit breaker. From my circuit breaker, I'm going over, I'm going to feed to the toggle switch. There's an internal circuit in here. They're going to turn anything on and off. So I'll just turn my battery power off and turn it on and off so you can see I've got my switch there. Turn my power back in. And from there, I go over to one lamp, all right? From the lamp, I'm going to go across to my black lead here, which just follows around here and goes over to the ground. The ground is at, the chassis ground is at the bottom. So that everything's in the chassis is going to be here. So it's real important to look at. So this is a simple series circuit. Now, the other thing is I might want to do is check my battery start, but I want to do my resistance testing first on this. So I'm going to follow my own rules. Power's off. I want to measure, I took one lead out, or isolated component. So I'm going to take on this board, if I get it up here right, and I'm going to turn my meter over to ohms. And if I'm looking at my meter at ohms, I'm going to see I've got 4.8, 4.7 ohms on that board, or on that component on the board. Now here's what you can look at. If you're going to play some games with your students, what you want to do is calculate the resistance of that, and then calculate what it should be with the circuit live. This is the only exception to Ohm's law that I know. When you fire up the circuit, it will change, because what will happen? I'm changing resistance in that bulb because I'm putting out heat. and I'm putting out light. It makes a difference in the process. So you want to make sure that you understand if the circuit's off, the resistance is there. When the circuit's running, the resistance will change on a bulb or an injector or something else. Injector should stay the same, but the bulb is going to change because it's generating what? It's generating light and it's also generating heat, and will affect the reading. So it's something you want to do with play with your students. Give them something to understand that that is one exception to the rule that I've always found. Now, I'm going to turn my circuit on, turn my toggle switch on, and now we have a light there. So if I'm going through the circuit, the first thing I always like doing is making sure that I have adequate supply. So I'm going to turn my meter on again. I'm going to put in the volts, and I'm going to take my black lead and just put it here, take my red lead there. That is my battery up here. That is my supply voltage. So I got 12.59 volts going across. I'm going to leave my black lead where it is. You do not want to be moving your black lead and ground lead. Once you get a good ground, leave it there. That's why I told you earlier, if you're checking on the back of the circuit and you're going to use the battery as a ground, you might have longer leads. So the first thing I want to do is come over before my circuit breaker. I've got 12.59 volts, so that means that if I was, just real interestingly, 12.59 here, 12.59 here. There is no resistance in this wire. So this, well, there's whatever, it's not going to have a voltage drop across the wire. I'm going to go after this, I'm going to go to my switch up here, and you notice I have 12.45 volts. Well, I have drop voltage across the toggle switch, and we had a couple of things we were talking before, the leads, what the resistance of voltage drop. So I'm going to put before and after. And you notice I got 0.1 volts, 0.14 volts that we dropped across that. I just want to show you real quickly, we can check the circuit. So again, take my black lead out, put it back to my good ground. And so I got 12.59, and after my toggle switch, I have 12.45. So I have used a little bit of voltage across that. I'm going to go from there, and I'm going to go ahead and pull my lead up, and I'm going to go across to my bulb. So I got 12.45 volts going to my bulb. And after my bulb, I have 0.02. So this circuit is a 12-volt circuit. That's a real good. So I notice I have no voltage left over. That's used most of the voltage. Now I can do a voltage drop again. And the way I would do a voltage drop is, again, now I have to move my lead. I'm going to do it in front of the bulb and after the bulb. So I dropped 12.45 or 12.44 volts. Well, that's not all the voltage of it. Where was the other voltage I would worry about? The other voltage was across what? The other voltage was across my toggle switch. So I know for a fact that's my voltage. If I want to see what I started out with, 12.59, I got 12.57. We moved a little bit, but if you notice they're going across the circuit, I could actually come over here. There's 12.58. This is ground on the chassis. So I have the complete voltage dropped across the circuit. Now, if I'm doing this, this is showing you the real easy way this circuit works. Now, the other thing I can do, I'm going to turn the circuit off for just a second. The next thing I can do is measure current. So what I'm going to do is do the feed side of the current. And we'll do this again. Got to move my lead. All right, and I have to put my lead to what? I have to do it all the way over to current. So I'm going to take my black lead and put it at the circuit breaker, and I'm going to check the circuit up here, and we're going to turn the circuit back on. And I have 260 milliamps draw. So that's 260. So if I was doing this circuit again, I'm going to turn it back off. I'm going to reconnect my feed side. If I reconnect my feed side, now I'm going to do what? I'm going to take over my lead, black's ground here, take my red lead, and I'm going to do what? Put it after my lamp. So I'm going to check the ground side, and if I come back over and do this process, turn this back on, you notice I have approximately, there's a little variance as the heat's on here, so I got 259 milliamps. I had 260 there. The lamp's not the same, you know, a little change in it. We're right between it. But in other words, my amperage is the same on the entry, of the circuit and to the ground side of the circuit. So the feed side's the same, the ground side's the same. I could go in the middle of the circuit and the amperage would be the same. There you go, 12.59, the same thing. Excuse 12.59, sorry about that. 2.59, so we got the same amperage draw across the whole circuit. What varied that, what took a while was for that bulb to get lit back up, showing the same process. So it's back up to full intensity. We have 259 milliamps on the feed side, 259 milliamps on the ground side. So that tells me this circuit is working properly and I have proper amperage. Again, amperages will be the same across the circuit, voltage will drop. That's what you have to look at in the circuit. All right, now what I'm going to do next, I'm going to stop here a second, and what I'm going to next, I'm going to feed a problem into this board and we'll repeat our test and we'll see what we come up with. I've inserted a fault in this particular board. Everything's turned on. You notice right now my light is off. Doesn't make a difference if my switch is on or off. The light is off right now. So the first thing you always still do, no matter what, you always still check your source voltage. And my source voltage is 12.60 volts. Now, I'm going to leave my black lead where it's at. I'm going to go through. And I'm going to hook up here 12.6. All right, so no voltage lost through this circuit. We had a voltage drop before. We have no voltage drop right now, so 12.6. I know where we're going with the circuit because I put the code in, but also it's a nice little thing to look at. 12.6 and 12.6, so on the ground. Now, what does that tell you up there? First of all, if you realize something, if I would fix this circuit, I didn't use any voltage, so that means this circuit is incomplete. Now, if I go to my ground, I got 12.6. So that tells me I have an open circuit somewhere here because I haven't used any voltage. There would be no amperage flowing through the circuit, and the voltage is there, but it's not being used. So if a circuit's complete, we always use some voltage. Now, right now I don't, so I'm going to come up over here and I'm going to take my red and black lead. I'm going to go over here and I'm going to my ground, and what have I got? 12.6. So if I was doing this, I'm going to move my lead back just one more, show you something up here. Now this might be a good idea right now for me to do one other thing. I'm going to shut the battery power. I'm going to shut the circuit down temporarily. And if I was doing this, what I might want to do is come back over and take my lead up here. I'm going to flip it over to ohms, and I'm going to put my alert on it. And you notice it says open circuit. So if I come over and move my lead again, black, I'm doing a continuity test. That's what this extra button here. Some of them will have a little bit of mark, so I got continuity. But if I go continuity from here to here, there is no continuity. So let me go back farther. There's continuity here. So I have, this circuit is complete. Circuit's complete there. So my problem is, right now, if I put the leads here again, notice I got it complete, move them over one, and go to my negative battery post. Notice this is open load. In other words, when we have the beeper working, we have continuity. The circuit is complete. That tells me right now I have a problem between the chassis ground and the battery negative. Somewhere I have an issue. I have an open circuit up there. It says open, but the other thing is the continuity tester is not beeping, so that circuit is open. That's a real quick way of determining we've got a problem here. So in other words, we've got an open circuit, nothing's being done with this circuit, no work's being done, so there should be no amperage flow through the circuit. There's no voltage drop through the circuit, so that's one other way you can do it. And the continuity test does work. I don't use it as much as I should because I process, but here's the deal. Again, I know for a fact I've got continuity here. Got continuity here, but I don't there. So I know somewhere between this point and this point, I have it opened. So that's how we can use a continuity test and on this particular board. Now, I'm going to do one more test on this board with another problem. We'll see what it works, or how it works and how it's going to be a little bit different, or how we can actually learn to test the car or the circuit correctly. And if you'll notice something at this point, I'm going to turn my circuit back on. Have my 12 volts. I'm going to do this a little again. My light bulb's out. So again, I'm going to check my circuit,
make sure I have proper voltage. And I have 12.60. Interesting. So I'm going to go before circuit breaker, 12.60. After the circuit breaker and switch, I've got 12.59. So I dropped a little bit of voltage right here. Just a little bit of voltage at this point. Now, take my lead off. Before my load, I got 12.59. After my load, I've got 12.44. Interesting. So if I'm going to go to my ground side, my little lead picked out there, I've got 12.44. So what would that indicate to most of you? First of all, if I was doing this particular circuit, and I've got 12.44 there, if I come back over and just flip from here, let's do this right, 12.44. So in other words, I have now a voltage drop. If I was doing the voltage drop on this, let's just do this real easily. If I go after this, I got 12.44. Should I have 12.44 after my load? Circuit is complete if I was doing this. What it tells me, I have high resistance on my ground circuit. Because again, after my load, I should have what? No voltage or less than what? 0.1, 0.2? Right now I got 12 on here. And one guy says, well, that's not realistic. Yeah, it's not realistic sometimes on some cars, but it is realistic to teach your student, I've got very near the same voltage, but I do have a different problem. That's why it's important to understand. So right at this point, before 12.59, 12.44. That tells me that that circuit is complete because I have used some voltage across the bulb, all right? And to make sure you understand, I'm not tricking you. The minute I turn off the load, it's there. So right now we go at 12.02, and almost you got 0.1 on the ground. So there's voltage kicking in. Now, the reason I did that is because you got two circuits here, and we always should check the circuit to be complete. We also should check the circuit for resistance. I could also check this and put a problem in on the toggle switch or something else on the feed. Most of the time I find the problems on the ground, so that's why I wanted you to kick this up. A lot of times you have a fuel pump that's not working correctly. A lot of times what you find out is a lot of times the ground side is where the issue is, where you got a ground connection on it. I've seen some Ford trucks where guys have put 3 or 4 different fuel pumps in them and turned around, all it was a ground connection on the fuel pump itself was the issue. They just use the amp probe for it. You always got to use more. So in other words, we have high resistance on the ground. And again, my problem's fixed because why my problem fixed? Right now I have what? 0.02. So if I had that problem again, the light went out, and what have I got now? 12.32, all right? So we got a little difference on it. But again, if you're looking at the readings, you need to look at the circuit. An open circuit, you will have what? Same voltage across the circuit. Anytime you drop voltage, that circuit's complete. So now you're looking at resistance or you're looking at other issues that might with the circuit. If the circuit reaches the same voltage going across all the way through, that circuit is open. If you have voltage drops going across, the circuit is complete. If you have more voltage left over after the load, either you got a bad load or you have what? Or you have what? You have a bad ground on the circuit. This makes a way of thinking about it, breaking the circuit down in sections to be able to diagnose it correctly. We're going to do some live testing with some sensors, simulated sensors up here. So first of all, I've got my O2 sensor up there, and if you notice my O2 sensor, I can see it's going rich, lean, and I can look at my meter and it's going rich and lean. When you're properly testing the O2 sensor, you probably should go about 2,000 RPM, and what you want to do is min-max, because some of your scan tools will allow you to graph it, but they don't always give you the proper readings. So what I want to do is just hit min-max, and when I'm doing that, I've got 9.24, and it's 0.004, and my average is 446. So this would be a good running car because I've got my readings up there that I need, and we're looking at it again. And to turn that back off so we get live readings, I just do this. Again, if I hit min-max, it's going to record. That's my max. There's my minimum, and there's my average. Real quick way of testing the O2 sensor. And you can verify this with your scan tool if you want to, and you can graph it. But this way,
I know what my average is. Now, why do you makes a difference what your average is? Your average is going to tell you if the car is really running rich or lean. If my average was 600 millivolts, I'm rich. If my average is 300 millivolts, I'm running lean. This is a really quick test on this. The other thing you can do is add propane, or you can add, create a vacuum leak to see if the thing responds real quickly. So this one's working fairly well. We know what we're doing there. So hit min-max again, and we go back to live readings. The next thing you might want to do is come out and check an injector. Now, what I'm going to do over here, go to the ground side of the injector, and automatically, and notice that I'm over on voltage range. So what I need to do is hit my range, turn the meter back off again, and kick back in. Whenever else, flip the meter off. So I'm going to hit my range up here one more time. And if I do this quickly, you notice I got 13 point volts. That is my voltage to the system. If I hit min-max, I'll have max 13.24 and a minimum is 12.96. So that means I did duty cycle and did some changes on it. Next thing I'm going to do basically is do this again, get back to live readings, min-max, and then peak min-max. Notice my meter went over. So my range is more than I need at this point. So I'm going to turn that back off. And I'm going to change my range if I can up here and make a little bit, maybe I hit the wrong button for range, guys. All right, there we go. And that happens. You're going to make mistakes on meters. Just if you are, turn the thing off, start over, or back out and start again. So what I'm going to do right now is hit min-max. And what does it read? 13 point. So there we go, live reading. If I hit min-max again, hit peak min-max, notice I got 36.8 volts, 37, excuse me. And there's my minimum 1.6 volts. And there was my average of the process. So again, this went to 37. Most of the voltage you're going to see is somewhere between about 35 and sometimes up to 100 volts on an injector. There are some that will do close to that. So in other words, I've done peak, min-max on this particular meter. Now, if I take this thing off, flip this again, and I've got the voltage up here, I'm going to go over and I'm going to hit hertz. And at hertz, it's going to give me the hertz on the signal, if you see that. And I can also come up here and duty cycle. Now, this is where you're going to have an issue up here. First of all, on the issue up here, the ping on the meter, that's actually telling you duty cycle. So if I was coming over here, sometimes I can change, you have to change your trigger. We'll see if this one changes trigger right now. It didn't. I'm going to hit. So if you were looking at a meter, I would want to go over and figure out how to change my trigger. If not, I take what I've got right now, 98.2, and I subtract that from 100%. What would that be? We're looking about, what, 1.8 milliseconds a time on my duration. Other meters will allow you to change the trigger, and depending on what you've got, guys, it would make it a little bit easier doing your diagnosis. I changed meters on you right now. This meter has the ability to change the trigger. So a lot of your meters won't do that. Some of them you will. If you have the ability to read your information, you have the ability to do trigger. So if you notice, I've got 1.7. That is the pulse width of the injector right now. So I'm going to move over here a little bit. If you look at the 1.7 and went to 1.8, now I'm going to rev the engine up. And let the engine come back down. You notice it went to 8.2 and pulse width on the injector. That would mean I have a snap, the car would be going rich. In other words, I'm looking at the information. This makes it a lot easier if you can do it, if you can change the trigger. I like using the one they can do this is a meter to look at it, guys, being able to change the trigger on it. You might want to look at your information because not all the now the DMMs will do it correctly. So again, this is what you would want to do to get your pulse width correctly. Notice the 1 meter, I would have to do math or find out how to do it properly. It was stuck, so it didn't do it. This meter automatically did it. And if you notice, the neat thing about it is if you look at auto up there and you look at it, it has a trigger over in this area over here, and the trigger says negative. Some of them will trigger with a positive trigger, some of them with a negative. If you can put it to a negative trigger, you will get the actual pulse width on the injector. And again, you would do what? Rev the engine up.
and let the injector come back down, and you would see the pulse width on the system. Most of the times, if you're alive on a car, it would go to 0 because you shut the injectors up on deceleration. But this really helps you out understanding that you need to be able to change the trigger to get a real good reading. All right, we're going to move over to some other testing right now. If you're looking at a sensor, you should always check all 3 wires. This is very important. So I'm hooked up to my throttle position sensor on the A terminal, connection up here, and you got a 5.01. I should have somewhere between 4.9 and 5.1 volts as my input to the sensor. That tells me right now that I've got good adequate voltage up here. If I had a ground issue or if I had a wiring issue, I wouldn't have proper voltage to the sensor. That's why you should always check all 3 wires. Next wire, I'm going to go to the B, and when I go to the B, I've got 0, 0, 0. All right, that's going to be my ground. I don't have any issues with the ground on this sensor. Now my next wire is C, and if you notice on C, I've got 0.44. Well, 0.44 is probably a good reading at idle or key on running up here. So what I'm going to do is rev it up. And you notice we went to 4.55 volts, 5.6 here. I can also put this down. Now the other thing I could do, which I'm going to do now, is I'm going to hit min-max one more time. .56, 0.44. And I'm not really worried about the average on that one, but again, it would tell me it's good. The other thing I want to make sure you also watch here, your numbers are updated 4 times a second. The bar graph at the bottom, depending on the system, is going to do 40 times a second. So if I'm watching this, I want to make sure that bar graph goes steadily up as across. So if we look at it real quickly, see it? At the bottom, move as slowly as I go across. And that's the wrong, and I'm in the setup here. Let's do this again. What did I do, guys? I messed up. All right, that happens. 0.44, all you do is, again, you push buttons and you start over. And you tell your students the same thing. They make a bad mistake on it, they mess something up, start over. It's called, start over is always a good idea. So we do 0.44. You watch the bar graph at the bottom. If the bar graph at the bottom would go up or jigger, I call it jigger, or you want to jiddle, or whatever you want to call it, where it would go up and back and forth and do this up here, that would indicate you haven't opened in the TPF sensor, so you would have an issue that you need to deal with. That makes it a little bit easier for you to understand. The bar graph, again, updates 40 times a second. The voltmeter updates 4 times a second on the numbers. So it makes it a lot easier doing your process. Now let's take another look at another sensor. We're going to go out and test the bus on this particular system. You want the system at rest when you're doing this. We have 2 120 ohm resistors. These are what's called terminating resistors, which means the signal is going to be going out, terminating, and we're going to be sending something back. So they're in parallel. 2 120 ohm resistors are parallel would give you 60 ohms. And if you notice, I'm at 62.1. That means that we're looking at a good resistance on it that circuits properly. Now, I have some connectors up here. Anything on the yellow up here is on the high-speed bus. Anything on the green is on the low-speed bus. So if I come up over here and I just decide to take the ECM connector off, notice what happens. I take away one terminating resistor, and now I'll have a 120, which means I have an open somewhere in the circuit. Now, if I turn that back on, we get it back to here. Now, the other thing is, what we're looking at is, I'm going to turn the power onto this unit. And you notice I still have 60 because the computers are down a little bit. I'm just going to turn it on and watch what happens. 2 things is going to happen. You're going to see this moving back and forth with the voltage, 300, the voltage is saying something up here, a little weird up here, but that's in ohms right now. If I would come back over here and I'm going to put this thing in voltage, and at voltage it says a 0.3, all right? But you notice something interesting. I have 0.1, which is the LAN voltage. That is the signal for the LAN circuit. That's a low-speed circuit. 6 and 14 are lit up, and those are the circuit that we're communicating on the CAN bus. All cars since 2008 must have the CAN bus, so that's my high-speed bus. Now, since I'm looking at this little process, I can look at this voltage a little bit. I'm looking at differential voltages up here. Pin number 4 and pin number 5. Pin number 4 and 5 would be the ground on the circuit. So if you notice, I got 2.65 volts on that particular circuit. That's on pin number 6. If I go on to pin number 14, we were going to have 2.34 with a little bit different voltage. But I know something's going up here. I could actually do something really weird. I just come up here and put this thing in hertz, and it's not going to give me a signal I can use. So again, I want to go back to my voltage and look at what we've got there. So looking at the voltage, I know it's there. Now, the problem about it is at this point, when we get into this, we have to start breaking out another tool to do more diagnostics. Some of your scan tools will give you what's called a topology map, and a topology map will tell you which computers are on the network. That's a really good thing to use. And if you know what's on the network, anything that's not communicating would be something that would give you a communication issue that you can show up here. The last thing I wanted to do up here is just something else I wanted to show you. If I'm going to come back in and I'm going to shut this thing down, turn my key off, and I'm going to go back over to 6 and 14 again, put this thing's in ohms now, and what have I got? 62. I wanted to make sure you see this. If I come over here, I'm going to take the ignition switch, I'm going to take it out of the circuit, and I flip it down. What happens to my ohms up here? Didn't change, because I'm on a different bus. My instrument panel cluster, not the same bus, all right? And radio connector should not be there. Nothing else is going to affect it. The only thing that would be affected would be on this yellow circuit up here. There are sometimes it bleeds over, but the way this is written, we're only going to worry about the yellow is going to be a high speed, the low speed is going to be your green. Now, that's pretty much what we're looking at for diagnostics, or kind of a way of telling you how to check some of the things on in the bus. Now, if you want to do this, you always got to make sure you do this. The system has to be at rest, which means the computers have to be quiet. The key's off, the doors are shut, nothing's working. It takes a few minutes for some of these computers to shut down. At that point, you should have 60 ohms. If you have the 120, you ought to immediately know that you have an open or something going up there. If you have ohms that are way down or have a voltage, if you had a lab scope on here, you would indicate you have a shorted bus. So it's real quick testing on the busing. I want to thank you for attending this webinar. It was fun for me to do, and I wanted to make sure that we all think about, and when we're investing our money in the digital voltometer or the DMM, whatever you want to call it, that you might want to rethink how you do it and look at the specs, look at what it would do for you, and you might need to think about it because that is your secondary tool along with your scan tool. Now, we covered how to use digital testing on it. We covered how to test on the board. We covered your circuits. We showed you how some circuits would be proper opens or grounded, high resistance grounds. We covered min, max, and average. We covered how to check your injector. We covered a lot of things up there real quickly. And if you have any questions, I'll open up the questions now.